given a force function, you can calculate how much work was done if you know the bounds AB, right? Now, the sheet has these on there, but it only has it in one form that like says, you know what we're gonna do? We're gonna shove it all together in one equation. All right? It's a little less than halfway down, and it says delta E. So delta E is your change in energy, which is also known as the work, which you can calculate if you take the antiderivative of the force dot dr, where they use r here instead of x because they're saying like it could be really in any direction. It doesn't have to be horizontal. So they use the r to say like it could be up, down, left, or right, or whatever. Cool? All right.
Are our only equations on this part
Yes.
of the sheet? Okay.
Yeah.
We'll never look at the electricity and
Oh, sick.
my roommate for next year is taking a physics class, an AP physics class where they do both mechanic and electricity.
That's disgusting.
And that sounds like he's like so sick of it.
Electromechanical engineering.
So I don't like when I have to stand and like talk and just like lecture. I don't really like it. It's not my favorite way to do it. I like to mix it up a little bit and have some discussions and have some fun and do some labs. It would literally be all day, every day, write down what I'm writing down. Solve a problem.
If you were a professor?
No, if you
No,
were
just
taking,
saying if it was.
if you were
a
taking
class.
the class that
Actually,
had,
that's-
that
Yeah.
had both sides of this. You would hate it, I would hate
It doesn't
it,
have
you
to
would
be
hate
double.
me, it would be awesome.
It's
Anyway.
like double swing.
It's
That would be awesome.
So,
My students would finally hate me for
We do like
So-
every assessment.
I have a feeling Mr. Penn doesn't care if students hate him.
yes and no. So, I mean, I love you guys, but my goal is to try to provide you the best learning opportunities that you can. So whether you like me or not, sometimes it can be easier for me to do that if we have a good relationship. But we're not like friends, right?
What?
I mean, I love you guys, but we're not like friends. You're like, we're not gonna hang out.
What?
I was just about to ask.
I was gonna invite you to my birthday.
That's why I came here.
I mean, it's fine, trust me. So work can do two things. One, work can change the kinetic energy. Does that make sense? This is actually a huge deal. This is called the very interesting name.
Whoa,
Whoa.
that's a
It's called the
lot.
work energy theorem. And it's the net amount of work done. The net amount of work done is equal to the change in kinetic energy of an object.
Is it net for the top one too?
Yeah, usually there's only one force causing that, but we'll just save that. This one's important. So if you visualize a situation where you have a block on a rough surface being pushed by a hand, right? And it's speeding up in this direction,
There's friction, there's mg, there's force normal.
right? So we got a lot of things going on here. But the change in kinetic energy would be equal to the net work done. So there's work by the hand. There's work by friction. That's going to be negative because it's in the opposite direction, right?
Yeah.
So would you just, never mind.
And that's going to be equal to the change in kinetic energy of the box after it moves some distance d. Right? So if it was frictionless, then the work by the hand would just change the kinetic energy.
Oh, so it's like force because work and
Yes. If there was no hand, it would slow to a stop, so the work done by friction would cause the change in kinetic energy. If it's moving at a constant speed and the kinetic energy is not changing, that means the work you're putting in by the hand is all being lost to thermal energy in the work done by friction. See how that works? So the change in kinetic energy is brought upon by the net work done. Is that cool? Work can also go into changing the potential energy of the system. If it's a spring, that's okay. If it's a gravitational field, that's okay also. These are both systems that we can deal with. So if you take a box, for example, and you move this box from here to here, okay, have I changed the energy of the Earth box system? Absolutely I have, because I lifted it up. So the work that I did is equal to the change in the gravitational energy. Is that cool? So this is where it gets a little complicated. Try to hang on. Because this is the work done by me. Okay? What direction did I apply a force?
Upward.
Up. And what direction did it move?
Up.
So what has to be true about that work? Is it positive or negative?
Positive.
It's positive because they're in the same direction. The angle between them is 0. Cosine of 0 is 1. Work done by me is positive. But in doing this, there was work done by the gravitational field.
And it was negative.
It's absolutely negative. How do you know it's negative?
Because F is
That's it.
negative.
That's right, because the gravitational field pulls it which way? Which way?
No.
Down, but it still moved
Up.
up. These are anti-parallel. The angle between them is 180.
Still-
Cosine 180 is -1. So the work done by the gravitational field is actually negative.
So we're net is 0?
So actually what's interesting is the net work is 0 because you start from rest and you end at rest. So the change in kinetic energy is 0
Yeah.
because the net work had to be 0, right?
Mhm.
So this is also the same as a spring. So if I push on a spring, I can do positive work on the spring because the force and the distance are in the same direction. True? But the work done by the spring is going to be negative because its force was out, but the distance, the change in the displacement was in. So that's how we end up with this negative thing that annoys me to no end.
I like that the back of the marker works on the way.
Did you have an old smartboard in this room?
Yeah,
He's like, I didn't use it.
I didn't actually. I always drew on that. Now they're like, "Would you draw on this, please?" I'm like, "Sure."
Sure.
So what we end up with, okay, what we end up with is this idea that the work is equal to the antiderivative of the force dx. True? You with me on that? And this could be equal to the negative potential energy function. Is that cool? Now, what am I going to do here? Okay, I would like to solve for x.
Why is it equal to negative u?
So, because the work done by the field or by the spring is opposite the potential energy. Right? So if it's the work done by the person, it would be positive, but because you're gaining potential energy. But if it's the work done by the spring or the field, then it's going to be negative potential energy.
So how is it work done by the field or spring in this case?
If we use this example, the box moved up, but the field pulled it down. So it actually, the work is negative, okay? Because they were in opposite directions. But let's just look at this, because I want to show you where something comes from. That's important. So calculus fans, I want to solve for f. What do I need to do to both sides?
Take the
For
derivative.
F, you mean, or for F?
I want to solve for f.
Oh, okay.
This is the antiderivative, so what do I need to do?
Derivative.
I got to take the derivative of both sides, right? Does that make sense?
Okay.
And the derivative of the antiderivative is just f, right?
Mhm.
Does that make sense?
Oh, it's du over d, yeah.
And I end up with negative du over dx. True? This should be on here, is it not?
We've talked about it in conference class.
Is it not on there?
Why couldn't it be though, like,
I guess it's not.
why couldn't it be like dw over dx then? W
Hey, man.
negative.
Hello.
If like negative potential energy is equal to work, could you also say that F is equal to the derivative of work?
Yeah, so remember, work is just the change in energy anyway.
Oh,
Wait, is this one on here?
So, I guess it's not, but this is something you absolutely 100% need to know.
So
So
it's
if there's one thing you need to memorize, I would say it's this thing.
so it's more like you're saying, like the work is equal to, and then there's two things. It's just like a visual representation,
Yes.
it's not math. Okay.
Yes. So because you may be given, okay, you may be given a potential energy function, and you need to know that the force is the negative slope of that function. Is that cool?
Yeah,
So this is something you absolutely 100% know. And we've actually done a ton of work on that.
yeah, we've done, yeah.
Right, and recently we've done a ton of work on that, so I
That's
feel
a
good about that.
potential energy slope.
What's that?
That's a slope for a potential energy graph.
Yeah, so, given, I tried to cut my finger off the other day. Not good.
That's still killing you.
So if this is x and this is u, right? And you have some function here. Okay. Let's say you have some function here, right? We need to know a couple things about the function. One, if I needed to calculate the force anywhere on here, how would I do it?
Negative slope.
It's the negative slope, right? Force equals negative slope. So a couple things that are interesting about this is if I look at the slope at any given point here, like there's the slope there, there's the slope there, there's the slope there, right? And what we notice is it's steep and negative, which means the force on the particle at this moment is actually large and positive, because it's the opposite
Yeah.
slope.
Yeah.
Here, it's still a negative slope, which means that the force is positive, but less, and it's getting less and less all the time.
So if it were going up, you would say force is going down because potential energy is increasing because the force is, like, let's say, you know, like when someone, I guess when someone's lifting, I don't know, that wouldn't make any sense.
So if you're lifting in a constant gravitational field, the field strength is the same.
Yeah.
So anyway, so this is interesting. So we look at this here, and then one of the things we talk about graphs like this is if we have a particle that's here, for example, let's say our particle is released here. Okay? If our particle is released here at x1 from rest, could you figure out what the speed of the particle was at x2?
I mean, I remember doing it, but. If they don't give you a function?
No. Whether they give you a function or they give you some numbers, right?
Yeah.
But the thing that you need to know is that the total energy,
Is equal to the slope.
the total energy is constant. So for location x1, so at x1, E is equal to u1 plus k1, right? And at x2, E is equal to u2 plus k2. Is that cool? But what do we know about the total energy? It's constant. Therefore, we say, well, that's fine. The potential energy at 1 plus the kinetic energy at 1 has to be equal to the potential energy at 2 plus the kinetic energy at 2. Is that all right? And we've seen a couple of examples of these, and I feel okay about these. And And the chance of this showing up are, I actually feel like kind of slim.
Oh, this is actually something I understand.
The chances of this thing showing up, it's like, really?
It's gonna be like all kinematics and no energy on the AP.
Oh, I would literally,
I would just get up at that point and walk out.
Well, I
It's
mean,
like when we looked at the
I like
data,
going
all of it
all
was like the stuff we learned in the last 2 weeks.
I mean,
and
it's like,
is our
one thing,
classroom.
it's like, my, what I could have met it.
I mean, I will talk to you guys
Where'd you get
about
on there?
what the
What?
test means and why it means it later.
What are kinematics?
I wouldn't.
Oh.
So like.
Get too excited about us.
What's the
I'm
design?
I think it's what the
I'm not
K
too
stands
excited
for and
about
the
this stuff.
K equals 1/2.
Oh, I think that's right.
like,
Yeah, that one half
topic
topic
for
or
kinematics is just that.
Yeah, that's just the equation.
Like all 4
You gotta
months.
know, man.
Wait, what's the?
Kinematics.
Kinematics is
K equals 1/2
I know
of
it.
V squared, dude. That was a
I
joke.
wonder if
That's
they've
Yeah, I
what
was
was
gonna
on the
say,
test.
comment.
I wonder if anyone's ever done that.
What's that? I got both ways.
Gone to a kinetic problem and just gave you guys one at the face.
Sorry, Andrew.
Or solve for the spring constant, like K equals 1/2 of V squared.
Why does every variable use the same thing?
I know, it's like, listen, man.
Yeah.
It's not, it's all contextual.
Oh, but
My
contextually, my
understanding
brain
is
I
hurts.
can't tell the difference between the lowercase and the capital.
I know.
Bro, the P is the worst.
That's why I
Because
decided-
P is hard to tell,
Yeah.
just the A whether it's capital or not.